In our next chapter, we will continue our focus on stereochemistry, this time by looking at chirality. And we can think of chirality as the property of handedness. So when you use the blue gloves in lab, it doesn't matter whether you put it on your left hand or your right hand. But if you were playing baseball and you had a baseball glove, then it does matter whether you put it on your left hand or your right hand, because a baseball glove has the property of handedness. If you hold your hands palm to palm, then they are mirror images of each other, essentially. But you cannot completely superimpose them on each other. Imagine trying to squish your hands together so that they take up the same space. Your fingers would line up on each other, but the palm of your hand would be lined up with the back of your hand, and the other palm would be lined up with the other back. So your hands are not superimposable. Now, there are important molecules that have this property of handedness as well. And that's what we will be looking at in this chapter. We're going to start out with an introduction to chirality, and then we'll be focusing on the properties of chiral molecules, looking at larger molecules, and then a number of miscellaneous topics. In this video, we're starting out with examples and definitions. Before we get into the details of chirality and this important type of stereochemistry, I want to take some time to convince you of why this is an important topic. And so I have a few examples, including enzymes, receptors, and medications. So looking over here, we can start out by thinking about enzymes. And enzymes are important biological catalysts. Enzymes will have a very specific active site, and a molecule, which is the substrate, has to bind to that active site. So let's say this schematic represents an enzyme active site. We have a circle, an oval, and a rectangle, and our substrate molecule has to fit into and bind to this particular active site. And here we have a pair of molecules that are mirror images of each other. So this would be like a left hand and a right hand. A pair of mirror image isomers that can't be superimposed on each other is called enantiomers. So if we work with this enantiomer and we try to fit it into the enzyme active site, we can see that the oval will fit on the oval, the circle on the circle, the rectangle on the rectangle. So this hand will fit into the active site. If we look at the opposite hand, so the mirror image, if we get the oval to line up with the oval, now we're trying to put the circle aligned with the rectangle and the rectangle aligned with the circle. So with enzyme active sites, one hand of a molecule will fit, but the opposite hand will not. And that's very important for being able to bind to the active site to carry out a reaction that might be part of an important biochemical pathway. Our next example includes a pair of compounds that bind to receptors. So this first one is called R minus carvone. The second one is S plus carvone. Throughout this chapter, we're going to see what the RS means and what the minus and plus mean. But notice these are very similar to each other, except for this difference right here. Now, this is another pair of hands. It's a pair of enantiomers. They're mirror images. Let's imagine that the screen is the mirror. If we take this molecule, slide it back behind, and this molecule, just pull it forward a little bit, and this will be reflected onto this. So R minus carvone, where we have this group coming forward, this is found in spearmint. And the S plus carvone, which has this group going back, this is found in caraway seed. So rye bread, for example. Now, although these molecules seem very similar, this difference is detected differently by receptors in your nose, in your taste buds. So maybe we like mint chewing gum or we have our minty toothpaste, but imagine if we were chewing on rye bread bubble gum, that wouldn't really taste that good. If we're enjoying a pastrami on rye, but it actually tastes like pastrami on spearmint, that's also not going to taste very good. And so the receptors treat these very differently. They will bind differently and they are detected differently, which is a good thing because I don't really like rye bread toothpaste. Our third example is a medication. This is called thalidomide. In the early 1960s, this was prescribed to pregnant women to help relieve severe morning sickness. The good news is that one enantiomer, or one hand of this molecule, was very effective at relieving severe morning sickness. Unfortunately, the enantiomer caused birth defects. And this was prescribed to pregnant women specifically. And so there were many children who were born with birth defects where their limbs did not fully develop because of the effects of thalidomide. This issue with stereochemistry, with handedness, it had a severe impact on these women and the children that were born to them, but it also led to huge changes in medications and the processes by which medications could be approved. And so now you either have to be able to make only one hand of a particular medication, or you have to be able to prove that if one hand is effective, the other hand does no harm. This need to be able to make only one hand of a medication, this led to significant changes in synthetic organic chemistry and the entire pharmaceutical industry. So here we have just a few examples of biomolecules or really large biomolecules where handedness is very important. But let's see how this idea of handedness can apply to smaller organic molecules. So can small molecules have the characteristic of handedness? Let's look at some very small organic molecules with just a single carbon. If we have, for example, 3 hydrogens and some X group, let's think about it in terms of its overall shape. And now let's represent this with a model. So here we have our carbon in black, our X group is in red, and then we have 3 green substituents. These are our hydrogens. Now, if we think about the mirror image, here is our mirror image where this is reflected into the mirror. Are these different hands that are not superimposable? Well, let's imagine now picking up this model and sliding it back over on top of this one. We need to twist it just a little bit, but if we line up the red on the red and the black on the black, by twisting, we can get the green on the green on the green. And so these molecules are superimposable. If they are superimposable, that means they are just the same compound. So it's just different representations of the same compound. So this does not possess the quality of handedness. What if we have 2 different substituents, X, Y? Now we think about this in 3D and we build our model, and then let's build our mirror image model. So blue reflects on blue, green on green, red on red, black on black, etc. Now let's pick up this mirror image and see if we can get it to superimpose on this one. Well, if we pick this up and then let's imagine rotating it around here so that we line up this green on this green. This green, we're twisting it around so it lines up on this green. Well, that puts the blue on blue and the red on red. So these two are also superimposable, and so they are the same compound. So this does not possess the quality of handedness. What if we have a carbon connected to 4 different groups? So it's connected to a hydrogen and some X, Y, Z. Here we have our model, and then this is the mirror image. Now let's pick up this and slide it over this way. If we line up the red on the red and the yellow on the yellow and the black on the black, then we are going to have the blue lined up with the green, and the green lined up with the blue. So these do not superimpose on each other. So these are non-superimposable mirror image isomers. So here, where we have 4 different groups attached to a carbon, we now have this quality of handedness, where we have a pair of non-superimposable mirror image isomers. Because they're not superimposable, that means they are not the same compound. These are actually isomers of each other, different compounds. So we see that it's not just large biomolecules, but even relatively small molecules can have this property of handedness. They have this property of chirality. So let's take a step back then and come back to this idea of isomers, and let's get some new definitions. So remember, isomers have the same molecular formula, but are different compounds. They have the same molecular formula, but they are different compounds. Isomers can be divided into constitutional isomers or stereoisomers. So constitutional isomers would have the same molecular formula, but different connectivity. Different connectivity makes them different compounds. So for example, we could have 4 carbons in a chain or 3 carbons and a methyl branch. These both have the same molecular formula, C4H10, but they have different connectivity. So these are constitutional isomers. Stereoisomers, on the other hand, have the same molecular formula, the same connectivity, but a different arrangement in space. And stereoisomers cannot be interconverted by rotation around single bonds, right? So we have to keep in mind the difference between stereoisomers and different conformations that we talked about in previous chapters. So recently we talked about things like cyclohexane, and we could have disubstituted cyclohexanes. Maybe we have methyl substituents that are cis to each other and methyl substituents that are trans to each other. Now they have the same molecular formula, the same connectivity, because the methyl group is at C1C2, C1C2, but they have a different arrangement in space because this one's coming forward while this one's going back. And they cannot be interconverted. So this is an example of a pair of stereoisomers. But we need to divide stereoisomers further into enantiomers or diastereomers. So enantiomers are non-superimposable mirror image isomers. In other words, they are stereoisomers that are mirror images of each other. Stereoisomers, so same molecular formula, same connectivity, different arrangement in space, and mirror images. Whereas diastereomers are stereoisomers that are not mirror images. Stereoisomers that are not mirror images. So a pair of mirror images that can't be superimposed on each other, this would be a pair of enantiomers. If we have something that's the same molecular formula, same connectivity, different arrangement in space, but they're not mirror images, those are diastereomers. So looking at the cis and trans, these are not mirror images of each other, so cis-trans would fall under the category of diastereomers. We are going to see some other types of diastereomers within this chapter. Now, all of these terms, isomers, constitutional isomers, stereoisomers, enantiomers, diastereomers, these are all terms used to compare two molecules, right? It's describing the relationship between two molecules. Now, it also would be helpful to be able to just look at not necessarily a pair of compounds, but just a single compound. Can you tell whether a single compound has the property of handedness? That's what we'll be looking at in our next video.